Number 2. The principle of complementarity. Why can a particle be both a particle and a wave at the same time? The complementarity principle states that opposing physical quantities can complement each other to form a unified description of a substance or system. What does it mean? For example, a photon is both a particle and a wave. Both aspects are true. The Möbius characters imagine the upper and the lower universe, and they come to realize that each and every one of us is a vast system, where the stellar systems of the lower universe serve as atoms. Therefore, even though the lower universe may be a vast cosmic space, it can be perceived as a small object to us. When we observe an object, we can see the entire space it occupies at a glance. So, we can also see the entire time the particles occupy. It's because space is time. Therefore, particles can be observed as particles in our eyes, but they can also be observed as waves because they simultaneously exhibit the appearance of vibrating or moving over a long period of time. Additionally, protons and neutrons are not individual parts of a nucleus, but rather the different ages of a nucleus. Protons represent a main sequence star during hydrogen fusion, while neutrons represent a white dwarf star after its death. We observe both protons and neutrons simultaneously because we can see all the moments which atoms exist. In reality, scientists have struggled for a long time to explain that the nucleus have the potential energy of two objects, despite the fact that the nucleus have the potential energy of a single object. They still refer to it as two objects. Why shouldn't we just consider it a single object? Another character asks a question. Electrons are particles that cannot be distinguished from each other because they have the same charge and mass. However, if you look at the planets in our solar system, aren't they all different? How would you explain this? Here's a hypothesis regarding that. Every point in our universe is in motion. Because of this, we cannot observe a single object, in this case, a planet, from a perfectly stationary point where we want to measure its velocity. Just looking at the Earth, its rotation. By continuously adding these velocities in this manner, we come to realize that we are flying through this universe at a much faster speed than we originally thought. No matter what method we try, it seems challenging to measure the mass of our planet from a perfectly stationary point. On the other hand, an observer of the upper universe, let's call her Scarlett, would be able to see the true velocity of the Earth because she observes the Earth from outside through the stationary boundary of our universe. Let's imagine Scarlett measuring the mass of the Earth. Scarlett could also observe our time, right? It's because space is time. In that case, from the perspective of the stationary boundary of the universe, Scarlett would be able to see our space-time and accurately determine our velocity and direction. She would simultaneously observe the mass and how much that mass curves the surrounding space-time. Similarly, she would observe the velocity and direction of Jupiter, its mass, and how much it curves the surrounding space-time. The hypothesis is that if we could observe all of these simultaneously, the masses of all planets would converge to a single value.